Good morning, fellow mathematicians. Welcome back to... Hey, is it you? Oh goodness. Oh, you have grown up so much. You are a really grown boy now. Let me take a seat first. Grabbing myself a little chair. I see. I'm getting old, it seems. Since I'm your dad and you are that age now, I don't even know if you can see me anymore. We really have to talk about it. So you see, you are that age now, and sometimes parents have to talk with their sons and daughters, girls and boys, Gucci's and Guccinas about the birds, the bees and the memes. And you are that age now. We have to talk about -112, my boy. Yes, the Riemann zeta function of -1 converges to -112, and we are going to show it today. And yeah, you are old enough, you are going to understand. Give me a second, I'm going to grab the chalk. I already have it in my hand, but I'm going to get it again. Bruh. Yes, I'm being serious. -112. This is our great journey today, and it's going to be fabulous because we can actually justify it with something we have derived before. So you see, I did Putnam integral videos a while back, and someone in the comments suggested me to actually look at a variant of this thing. Namely, we had an integral from 0 to infinity of x to the s-1 power over e to the x plus 1 integrated with respect to x. We arrived at some really weird solution, so take a look, and into the description there will be a link to the corresponding video. We were actually arriving at, okay, so we had our boy the gamma function, that wasn't any surprise at all. Then we had our boy the Riemann zeta function of s, but also we had some really weird term by rearranging this alternating Riemann zeta function. It was 1 minus 1 over 2 to the s power, but also we had a 2 up here. Okay, I actually have to think about what we got. I didn't explicitly say in the video what this right here actually is, but this thing right here is actually known as the Dirichlet function of s. And this thing right here is pretty damn important. In the normal case, our Riemann zeta function only converges for values of s being strictly greater than 1. But what we can do, we can analytically continue functions and their Taylor series expansion to hold for more values of s, for example. So just imagine you have some certain function and you have a certain radius of convergence. So here's a certain region for which our function will actually converge for. But now we are going to take a look at one of the points right here at the arc, for example, of this region. And now we are going to analytically continue this thing to hold for a bigger region. So now it also holds for this region, and overall our function holds for this region. Meaning we can extend our Riemann zeta function to also hold for negative values of s, or for complex numbers, for example. Key to this thing is the Dirichlet function, okay? Like I said, I didn't explicitly say in the video that this is the Dirichlet function because I wanted to get to this point in a different video. But this whole thing gave me the idea to basically plug -1 into here and arrive at something cool, because if we can analytically continue this thing and we use the Dirichlet function to analytically continue our Riemann zeta function, then yeah, it does hold. So we're going to play around with this thing, plug in s being equal to -1, and then we are going to basically arrive at -112. Are you ready, my sons and daughters? We are going to get started now. So, what I would like to do is boring integration by parts. You wouldn't have guessed that probably. So, we need something to differentiate and something to integrate. I guess you thought this is going to be more exciting, but it is what it is. We just take what we can actually get, okay? So plus minus plus. And I don't want to be like a certain person I don't want to talk about on this channel anymore because this pussy blocked me. Two pussies actually blocked me everywhere it seems. So never mind, fuck off. I just don't want to magically summon the Ramanujan Summation Formula from somewhere and say, oh, well, -1/12 is an integral.
Now for one of mathematics' most basic tricks, pulling a meme right out of a hat. Nothing up his sleeve. The hat is empty. He unfolds the red scarf. This is merely a diversion. Watch closely. He reaches into his hat and...
Yeah, that's not something I want to do. I want to start somewhere where it does make actual sense what we derived before. And this right here, I hope it does make sense to you guys. So I don't want to be like a certain channel because he's just summoning stuff somewhere in his video and then he thinks he's fucking cool. So yeah, what do we actually integrate and what do we differentiate? I guess I need more space for the differentiation. We are going to integrate for starters x to the s minus 1th power. Okay, integrating x to the s minus 1th power. That's just a polynomial in s, integrating this, raising the power by 1, so 1 over s times x to the s power. Integrating this a second time, and maybe you can already see where this is going. Leaves us with 1 over s times s plus 1 times x to the s plus 1th power. And you see, if we plug in -1, then this x is actually going to vanish and it's going to end up with being a really easy integral. So this right here actually works wonders. Let us continue. So differentiating 1 over e to the x plus 1. I'm going to write it like this. This is e to the x plus 1 to the -1th power. If we differentiate that, drag this to the front, reduce the power by 1. So this is going to give us negative e to the x plus 1, negative squared, and then take the inner derivative, which is nothing but e to the x power. Then differentiating this a second time is going to be quite a mess. We have to make use of the chain rule and the product rule whatsoever. So let's start off with the easiest part, namely differentiating this part right here is going to be just this term. So negative e to the x over e to the x plus 1 squared. I'm going to put it like this. And then next, we are going to drag this -2 down, reduce the power by 1, leaving us with +2 times. Okay, this is going to stay how it is, kind of. I'm going to write it out at first. Over e to the x plus 1 to the 3rd power, but also taking the inner derivative times e to the x. So e to the x times e to the x is e to the 2x power. I'm being a little bit speech retarded today. I don't know why, it sometimes happens. Yeah, how can we continue from here? Well, we can, you can also make use of the quotient rule. I just don't like that thing, so I like deriving stuff using the product rule. So you can advance this by e to the x plus 1 over e to the x plus 1, leaving us with, on this term, okay, I'm going to put it here, 2 times e to the 2x. If we multiply this right here by e to the x plus 1, it's going to give us negative e to the 2x, negative e to the x, over e to the x plus 1, to the 3rd power. And you see, this and that is going to cancel out here overall. And you can basically factor out a factor of e to the x right here. I really don't care. Yeah, you can also write it as e to the x times e to the x minus 1 over e to the x plus 1 to the 3rd power. No matter what you do, it is what it is, and now we can actually finish our integration by parts, meaning multiplying this together, and taking the integral of this thing multiplied together. So on the first occasion, we are going to end up with 1 over s, x to the s power, in this case, just s power, over e to the x plus 1. From 0 to infinity. We are going to talk about convergence in a second. It's going to be quite obvious. I'm going to give you a little example right here. Also multiplying this together. So this is going to give us -1 over s times s plus 1 times x to the s plus 1 power over e to the x plus 1 squared, and also we have e to the x right here. Okay, this is what it is, and also we are going to take the integral of this multiplied together. That's a lot of handiwork right here, I'm terribly sorry. Also we have to evaluate this from 0 to infinity. Also we had the negative sign right here evaluating to a positive sign. Okay, don't want to do any mistakes, even though this really doesn't matter right here, the sign, but never mind. Okay, on here we are going to get, this is going to be positive. So positive integral from 0 to infinity of 1 over s plus 1. After that we are going to get x to the s plus 1th power, then e to the x minus 1 over e to the x plus 1 to the 3rd power integrated with respect to x. There was a lot of work up until this point, but never mind. Now let us talk about convergence, and for this we are going to take a look at lower bound. So you see that's an easy polynomial in x, so on all the 0 terms it's going to vanish. What about the infinities? Well, you can take me by my word here, or you can do L'Hopital several times. If we let x approach infinity, this chunk is going, so down here in the denominator, is going to grow way faster than our numerator. So x to some power is going to grow way slower than something to the x power, except for 1 to the x power. Okay, so on those infinity terms is actually going to go to 0, but I'm going to show you that this more complicated term, I would say, goes to 0 in the limit, and then you can also do the same spiel for this thing right here. Okay, let us do this really quick. I just wanted to talk about it because this right here is a math talk, this is math snacks for some reason. And here, now I would like to simplify this a bit more. You see, 1 over s times s plus 1 is just a constant. We don't want it to be equal to 0 right now. It really doesn't quite matter for our purposes at the moment. So we are going to multiply both sides by s times s plus 1. I want you guys to recognize what gamma of s actually is. This is nothing but s minus 1 factorial. So if we multiply s minus 1 factorial by s times s plus 1, it's going to give us s plus 1 factorial, which is nothing but gamma of s plus 2. Okay, just keep this in mind. That's equivalent to saying, right here, we are going to get gamma of s plus 2. I'm going to put it like this, resulting just from multiplying this by our gamma of s. It's just a recurrent relation, so gamma is defined recursively, that's why we have this. And then Dirichlet of s being equal to some integral from 0 to infinity of x to the s plus 1th power, e to the x plus 1, minus 1, I'm terribly sorry, over e to the x plus 1 to the 3rd power integrated with respect to x. Now we are basically done. So this thing right here, once you get rid of our x, I told you the idea at the beginning, is going to result in kind of a standard integral. It's not too hard. Also, we can actually evaluate this side then if we plug in -1. So that's what we are going to do next. And we are going to evaluate this, and trust me, we are going to end up with our desired, in the normal case, divergent result. Daddy here. So, like I said, it's going to result in a standard integral. And at first, I would like to plug -1 into everything right here. Okay, so right here, if we plug in s being equal to -1, we are going to get, okay, at the moment Dirichlet of -1. What this is, we are going to talk about in a minute, or a few minutes. Then we are going to get gamma of 1, 0 factorial is nothing but 1. Okay, we got rid of that, that's good. Also, we have an integral from 0 to infinity of, if we plug -1 into here, that's x to the 0th power, we are going to get rid of this. So e to the x times e to the x minus 1 over e to the x plus 1 to the 3rd power dx. And the basically easiest thing to do is to get rid of our e to the x at first. So why not introduce a substitution, e to the x being equal to t, for example. I'm going to put it here actually. Let t be equal to e to the x, meaning dt is nothing but e to the x dx. and I didn't think that would be any good, but having this factor of e to the x on the outside is actually quite convenient right here, because e to the x times dx is nothing but our dt. Meaning we are going to end up with, if we plug 0 into here, then that's e to the 0th power, this is 1, so our integral starts at 1. That's an ugly integral sign, oh goodness, that's not so nice looking. If we let x go to infinity, t also goes to infinity. Easy as pie. Like I said, e to the x dx is nothing but dt, then we are going to get t minus 1 over t plus 1 to the 3rd power dt. And you see, this is something we can actually work with. And I invite you guys to do partial fraction decomposition, for example, but I would like to go with an easier way right here. And now you can be smart in the comments once again. And Daddy, don't you see it? You can advance this fraction by something. Oh, I'm so smart. I really don't care. I'm doing it my way, you can do it a different way, and if you don't like the video, then please feel free to dislike the video. I really don't give a shit. Best regards, Papa Flammy. Don't be such a smart ass. Everyone is smart on the internet, you know? So everyone can act like they are really, really smart on here. So we are going to break this up into 2 integrals. Under the condition that this thing converges, it does converge to a certain value. At least we are going to assume it. We're going to break this up into the integral of t over this chunk minus 1 over this thing, okay? 2 integrals, 1 from 1 to infinity, t over t plus 1 to the 3rd power, integrate with respect to t, and a negative integral 1 to infinity of 1 over t plus 1 to the 3rd power, integrated with respect to t. And maybe you see it, maybe you don't, but this thing right here is basically just integrating a polynomial, so we can introduce a new substitution. Let u, for example, be equal to t plus 1, okay? Meaning du is nothing but dt, so that's easy. But now our new integral that we are going to get is actually starting at 2, because if we plug 1 into here, this is going from 2 to infinity. So when t approaches infinity, u is still infinity. On here we can basically do the same thing. I would like to do this a bit differently. Let's say t plus 1 in this case. Yeah, no, we are going to do the same thing. So on the second integral, we are going to say let t plus 1 be equal to tau, for example, okay? Tau, we are going to do it. Then t is nothing but tau minus 1, okay? This does work out. And also dt is nothing but d tau, okay? Also, upper and lower bounds are going to be the same thing as on this one. Meaning right now we have 2 integrals. Integrals, once again, from 2 to infinity of, okay, this is going to give us tau minus 1 over tau to the 3rd power, integrated with respect to tau, minus, and now an integral from 2 to infinity. This is going to give us u, 1 over u to the 3rd power is u to the negative 3rd power du. Timo just came in, I'm terribly sorry. That's why I did stop for a second there. I already heard him walk towards the room. Okay, integrating this is quite easy. We are going to raise the power by 1 and we are going to divide by this new power. So this thing right here is actually going to be, okay, I'm going to write it out. This is negative 1/2 u to the negative 2th power from 2 to infinity. On infinity, you might notice that this is going to go to 0, so this is good. And if we plug 2 into here, this is going to give us second part of integration, positive, so positive 1/8. But here we have a negative sign, so negative 1/8 overall. Okay, also we can split this integral up, just like we did up here, into 2 new integrals. Okay, bear with me for a second here, we are basically done. Meaning, eta of negative 1 is now negative 1/8, just like we get it, plus an integral from 2 to infinity, yes, of tau over tau to the 3rd power. Yeah, I know we can cancel out some stuff. And a negative integral from 2 to infinity. Same spiel as before. So this is going to give us tau to the -3 power. This thing right here is nothing but 1 over tau squared, leaving us with tau to the -2th power. I'm wondering right here, here's basically stuff going to cancel out. Also, I forgot, oh no, there's a negative sign right here. So this thing right here is going to variate to the same thing as here. So once again, -1/8. We have talked about this a second ago, and integrating this thing is going to leave us with, okay, raising the power by 1, so -1/1, never mind, tau to the -1th power, from 2 to infinity. This is going to vanish on infinity, and here we are going to get -1/2. Okay, +1/2, because that's the second part of integration, +1/2. So we are going to get -1/4. Okay. 1/8 plus 1/8 is 1/4, and then +1/2. 1/2 is 2 over 4, so this is going to result in 1/4 overall. Okay, so we now know that our Dirichlet of -1 is nothing but 1/4. But what is the Dirichlet function of -1? Well, we had an initial definition for this thing. This was nothing but Riemann zeta of -1 in this case, times 1 minus 2 over 2 to the -1th power in this case. Meaning, this thing right here is actually, okay, we can take the reciprocal of 1/2 down here, leaving us with 4. 1 minus 4 is nothing but -3. -3 is not equal to 0 if you trust the Peano axioms and the extension to the negative integers, meaning we can divide both sides safely by -3. Riemann zeta function of -1 is 1/4 over -3 is going to result in -1/12. The meme, our Lord and Savior -1/12. Proven live here in this video on the Campus Golem in Potsdam by Jens Fehlau. I thank you guys for watching. If you did enjoy this little math snack, this quite long one once again, by those teachers I created, support channel on Patreon, click on those Quora questions I post from time to time. Also, just share those videos everywhere. If you really did enjoy this, then feel free to share it, because I'm trying to put a lot of effort in my videos, and it's kind of worth it in the less time once again. I thank you guys for watching, and up until the next video, have a flammable day. Love ya, my boys. Ciao.